Looks like we have folks from around the world. So good evening, good morning, good night, wherever you are in your day. I will be managing our webinar today. So if you have any questions, just drop them into the Q&A panel, and I'll try to call those to the attention of our presenter. If you're having any issues with the broadcast, please let me know. Things look good on our end, but they always do, don't they? We'll start in about 2 minutes. Give just a couple minutes for anyone else to jump in. All right, we'll go ahead and get started. I see some more people joining in. Thank you for coming out today. My name is Andy Creekmore. I'm a professor and chair of the anthropology department at the University of Northern Colorado, located in Greeley, Colorado, about an hour north of Denver, on the beautiful plains of Colorado. We've got beautiful weather today. We're conducting our workshop and testing outdoors for extra COVID-19 social distancing. This workshop is sponsored by the National Endowment for the Humanities as part of a preservation assistance grant awarded to our institution. We are interested in testing our collections for any old curation treatments that might have involved arsenic or lead that could create toxins that would be a concern for handling. So that is the purpose of our XRF work here on campus, but we're fortunate to have Dr. Lee Drake, who's going to speak to you today about the science behind XRF testing and how it can be applied. He has his PhD from the University of New Mexico, and he runs a company that has software that develops artificial intelligence to interpret spectral data for just these kinds of instruments. So I'm going to pass it over to Lee now. He's going to speak to you for about an hour or so. Then we'll have a break, and then we will be live streaming testing of our collection for anyone that wants to just pop in and see what we're finding, what we're not finding, ask questions, and so forth. We really want everyone to learn a lot today and get your questions answered. Thank you for participating.
I think I'm unmuted. So we are socially distanced here at the University of Northern Colorado. Andy is over yonder. I first want to say I hope all of you are safe and doing well. I know it's been a hard 6 months for everyone. And, you know, both Andy and myself are available for any questions that you have during this. Feel free to enter questions as we go along. And there is a chat function here, I think, that works pretty well. We'll have people monitoring that. My objective today is to kind of begin with an introduction on how we use XRF and with some basic examples. And then later this afternoon, we're going to go through and look at various objects with cultural heritage. Now, we wanted to make this an open event for everyone to enjoy. But at the same time, the thing to keep in mind is that we are trying to fulfill the purposes of a grant at the same time. So you might see us really zone in on a couple different features here and there as we continue. If there's any problems with the audio or the video, please let us know. We're very new to this. This is my first time doing an all Zoom workshop. If it works, great. We might think about doing some more in the future. But we hope this is useful to you. Just a quick mention too. I have a website, www.xrf.guru, G-U-R-U, and this has various tutorials, published academic papers, and all of that for how to use XRF spectrometry. And you're always welcome to email me at b.lee.drake@gmail.com. I know I met many of you when I worked at Brooker. Unfortunately, I don't have a Brooker email anymore, so any emails there enter a black hole that never return. But yeah, b.lee. You can reach me. So without further ado, we're going to try and share this screen, and we're going to the presentation. X-ray fluorescence with a focus on quantitative and qualitative analysis of artifacts and cultural heritage. And we are holding it here today at the University of Northern Colorado. What I want, do you see my screen? Okay, are we good? All right, good. Here we have the spectrum of visible light on a tropical ocean. I'm starting with this because I think it is very important to work from, as an archaeologist, it's always important to work from known to unknown. So, make sure that we know where we're starting from. And visible light is what we all have the most experience with. So here on the x-axis, you have the wavelength in nanometers of light, ranging from 300 to 1,000 nanometers. And then on the y-axis, we have spectral irradiance, but for simplicity's sake, you can think of this as the quantity of light. Now, one of the questions that always bugged me when I was a kid was, why is the sky blue? Because why not green? Why not violet? Well, the answer is in this graph. If you look very carefully, what color is the highest point on this graph? And if you look at about between 500 and 450 nanometers in the blue zone, our maximum peak is in blue. That is why Rayleigh scattering makes the sky blue, right? As you can see behind me. So the key is all of these colors scatter elastically. There just happens to be more blue, so that dominates. Up until sunset, when the angle of the sun changes and we start to see other colors. One other favorite segue I have in this is, well, we'll get to that in a second. It explains why plants are green. But this is the basic nature of light right here. The parts that we see are about 700 nanometers to about 400 nanometers, red to violet. Everything that has a higher wavelength than red, we call infrared. Everything that has a lower wavelength than violet, we call ultraviolet. But these names make kind of seem strange, right? Why is ultra with the low numbers and infra with the high numbers? Well, that's because a lot of physicists will discuss this instead in terms of energy. So in this case, instead of nanometers or wavelength, we're discussing the energy of particles. So this is very much on the particle theory of light phase, which anyone in XRF is a partisan for. So we have red at 1.7 electron volts and violet at 3 electron volts. Now, ultraviolet makes more sense because it literally has more energy. Infrared has less energy than red. And this is the full spectrum of light that we see. And then blue is the highest point here. Now, why in the world how does X-ray fluorescence play into this? Well, just like color fluorescence, we're going to have the physical manifestations of fluorescence. But instead of 1.7 to 3 electron volts, we're going to be working with 1,000 to 40,000 electron volts. And instead of colors like red, green, and blue, we're going to have colors like sodium, aluminum, phosphorus, and sulfur. And these can tell us the composition of objects. It can also tell us about the substrates that are on top of objects. It conveys a great deal of information about the objects we work with. The one thing to remember, and this is really important, because many of us are familiar with analytical testing in a laboratory framework, but when we're doing qualitative analysis, especially on objects that we're not trying to alter in any way, we're really looking at colors. And these colors can be part of what the material is made of, or it can be colors of residues or treatments on the object, say arsenic put on a taxidermic object. So that's just an example of how X-ray fluorescence works. So to dig into this, we're going to discuss the physical manifestation of color in our day-to-day life, and then we're going to take these same principles and use them for X-ray fluorescence. So that way you have a sense of where this data is coming from. Now, color is fundamentally a fluorescence process. A photon is emitted from a source. Now, in the case of this workshop, we are outdoors because of the viral apocalypse surrounding all of us. So all of our light is coming from the sun, and thus it carries that same spectrum that we saw earlier. But here's the thing. Not all spectrum are equal. Some light sources send out different types of light. So here I am sharing the laboratory of a museum that will not be named. And this workspace is divided into two different groups with two different leaders. One on the left decided that they wanted to use full spectrum LED bulbs. The one on the right decided that they wanted to use regular fluorescent LEDs or fluorescent lights because we're on a budget. So what you notice is to the right, you've got a yellowish skew. In fact, if you look at the filing cabinet, to the right, there's a yellow skew of everything. What I want you to focus on is the recycle bin in the far back there. It's got kind of a dark color, but in the United States, recycle bins are always blue, or often blue. If you look on the left, I don't know if I can use a laser pointer here. If we look over to the far left, you can see a little blue triangle sitting on the table on top of a box, and it's a very bright blue. The reason the blue comes better through the full fluorescent view is because higher energy photons in the ultraviolet range are actually getting through from that light bulb. So as a result, we see the full spectrum of color. Whereas, yellow on the far right, if you're consistently surrounded by yellow or by fluorescent, or even worse, those old incandescent lights, you get a really strong yellow-orange hue, which, still inspires some people to, paint themselves as if they're always in that light all the time. So that is the basics for how color fluorescence works and where the source of light comes from. The source of light has a great deal of control over the type of colors that you see. Now, that's not the whole story, though, because the light has to interact with something. And in the case of color fluorescence, it is interacting with the outer electron structure of the molecules in a sample. So what do we mean by that? Well, what we mean by that is we have the photon source, which sends in an incoming photon, in this case portrayed with the color yellow. This is then absorbed by an electron, which then takes in all that energy, because remember, light is energy. So the electron is now overcharged. It has too much energy. It got too greedy too fast. I always like to think of this as like someone winning the lottery. You just win $100,000. Well, what happens? We buy a new car. We buy a new house. So that money leaves our hands pretty quickly. And so then we have a photon that is fluoresced. And this photon has one rule. It must always have less energy than what was sent in. So just to go backwards, the incoming photon was yellow, which has an energy of around 2.3 electron volts, and we get red, which has an energy of 1.7 electron volts. It's inefficient. This is what makes X-ray fluorescence different than. This is what makes X-ray fluorescence fundamentally different than reflection, because energy is not being returned the same as we sent out. So you must always have less energy than was originally sent in. Which brings us back to this graph here. Earlier I mentioned the sky is blue because we have all this fluorescence occurring in the 2.6 electron volt range. And that lets us see, this is the color blue. But why are plants green? Well, plants are green because they take in that blue light. It's the most abundant. So they absorb the blue light, and then the chlorophyll molecules absorb that energy, but they can't hold on to all that energy. So they release a lower quality of energy, a lower energetic light. And that, to our eyes, is the color green, which is at about 2.4 electron volts of energy. So blue goes in, activates the chlorophyll, chlorophyll does its thing, green comes out as the residual, which is why plants are green. And so that gives you a sense of how the system works. The key rule here is the energy you see is always less than the energy you sent in. We cannot make more. If we could, then we'd have Star Trek technology and we could travel between the stars, because we'd be inventing energy out of nothing. But here we see how that works. So in any case, that is the basics of how that process works. A photon goes in, electron absorbs it, and it releases that pent-up energy. So now we have two steps completed. We have a photon that came from a source. We have an interaction with a molecule. But in order to make any sense of this data, we have to have some kind of receptor that we can use to perceive that color. In the case of visible light, that is our eyes, which have been honed over 500 million years of evolution. Now, the way to think about this is, here's our spectrometer plot. On the x-axis, we have our energy in electron volts. And on the y-axis, we have our photon intensity. This can be any unit. Sometimes it's a radians, sometimes it's counts per second. But the key thing to keep in mind in all these spectrographic views is that we're dealing with a quantity of photons measured. Red in this case would simply be a distribution of photons that have an energy that averages around 1.7 electron volts of energy. Green would be around 2.4, and blue would be around 3. So you can almost visualize these colors as peaks in a graph. Now, why red, green, and blue? Well, because that's the receptors we have in our eyes. When we see color, or at least most of us see color, we typically have 3 types of cone cells. One that can detect blue, one that can detect green, and one that can detect red. And because I'm a bit of a geek, I went through, dug up the literature, and I wanted to plot this in electron volts in the same way we think about X-ray fluorescence. And so here we have that graph. So here you can see the short cone cell, which detects the color blue. By the way, the names here indicate the mechanism that's happening here. The physical height of the cone cell basically influences how the molecule retinin can pick up the photons. So we've got our blue cone cell, which has a maximum sensitivity at around 2.8 electron volts. We have our green, which has a maximum sensitivity, not quite to 2.4, but just below it, around 2.3. And then red, which maximizes out at 2.1. Now, when you look at this, one of the things I find striking is the blue one obviously is very different, but the red and green ones are really close by each other, aren't they? What's going on there? Well, it comes down to a specific adaptation that we, as members of the primate family, have. Now, if you have a dog or a cat, they can't see the same colors we can see. They can't tell the difference between red and green. They typically have a short and a long cone cell, so they can see blue and they can see red, or something closely approximating what we see as red. The reason we can see green has to do with our evolutionary ancestry, because primates tend to eat fruit, and fruit tends to be, when it's ripe, red, and it tends to be buried in bright green trees. And remember, the trees themselves are green because the sky is blue and feeding in that. So the reason we evolved the ability to differentiate red and green is because for our ancestors, it gave them a critical survival advantage to be able to tell the difference between fruits and green. Now, it might only be 1 or 2 seconds of looking, but when you're competing with other individuals for food over millions of years, that's enough to spur evolutionary change. And in this case, what happened is that the genes for the long cone cell duplicated, but with a slightly different shift in their sensitivity. Now, interestingly speaking, this process is still happening with primates. Evolution is a verb, not a noun. So there are some human beings who can't see all 3 of these colors. Some men typically only see blue and red. That's because it is an X-linked trait. And men, unfortunately, don't have 2 X chromosomes. They only have 1, so they don't have a backup. On the other hand, there are some women who have the ability to see 4 colors. They're tetrachromats. They have an additional cone cell that fits between the medium and the long that lets them see shades of orange that most humans simply can't see. So this is still a process that's happening. At any given time, any number of individuals will have slightly different variances in this. So in any case, that brings us to the importance of detectors. So just to recap, we have 3 key steps. A photon comes from a source. That emitted photon interacts with the atoms, with the electrons in a sample, and then we have to have a detector to physically see it. Now, in X-ray fluorescence, we have the exact same process. And here, I'm actually going to stop screen sharing. And then, quick question, I'll need a confirmation on this from Andy. If I am talking, is my video the main one on the screen right now? Do you see me? Great. So what I'm going to show you now is the XRF. So can everyone see the XRF? Now for XRF, the one complication we have is all three of these steps, photon source, interaction, and detector, have to be handled in the same object, which is what makes handheld XRF so incredible. The way this works is we use geometry. So inside the instrument that I'm holding right now, we have X-ray tube, which is angled right alongside where my hand is, and then we have a detector right here. So we make a triangle, and then the triangle has a focal point right on the surface here. Raise it higher? Yeah. So then the X-ray tube is here, detector is here, and then right here along the flat is the main object, is the focal point where we measure. So this way we can have the photon source and we can have the detector all in the same equipment. There are some compromises with this, by the way. If we have this kind of geometry, the X-rays tend to penetrate deeper into the sample. And so what that means is there's a lot more scattering happening of the kind that we typically don't want with X-ray fluorescence. It's what we call backscatter. It's sometimes referred to as Bremsstrahlung radiation, which my colleagues inform me I always mispronounce. But that basic radiation creates a lot of the interferences. Now, that said, as I've learned in my company, as I develop artificial intelligence to study it, that backscatter actually has a lot of information about the compositional properties of the sample. So it's not error, but it's also not easily interpretable. What we're typically focused on is the fluorescence peaks. Now, if you wanted to get perfect fluorescence, what you'd want is a right angle. So you'd want to basically skip the photons like a stone across a lake. That will give you minimal backscatter and lets you see parts per billion level in objects. And Brooker, for example, makes some objects, or Brooker makes some equipment like the T-Star and the Picofox that have that 90-degree angle so you can see part per billion analysis. With handheld XRF, the compromise we make is the angle is optimal for portability, but it's not optimal for detectability. So we're typically limited to parts per million level analysis. Though in some cases with plants, you can get to around 500 parts per billion if you're looking at strontium or zirconium or elements such as that. But in any case, that is how this equipment functions to accomplish that data end. We're going to jump back to the presentation, and if you'll bear with me, I'm going to confirm with Andy that we're here. You can see it? Great. So in any case, that is the basics of that. The tracer back where it belongs. And let's continue. Now, the one big difference that's going to happen between X-ray fluorescence and your eyes is which electrons we're interacting with. So real quick, here's our geometry, and then we're going to jump back to here. The big difference between X-ray fluorescence and your eyes is which electrons they interact with. When we're dealing with when you're dealing with X-ray when you're working with X-ray fluorescence, you're digging deep into the atom because you're dealing with extremely high energies. We're looking at anywhere from 1 to 40 electron volts of energy. When you're dealing with your eyes, it's the very surface. In fact, it's not even really the atoms that you see. When you have a pure element like iron or manganese or any of the others, they typically just kind of look dull and gray to us, nothing too special. So it's really, so what you're typically seeing when you see visible objects is the electrons that are bound in some kind of compound state to then be able to see those interactions. With X-ray fluorescence, these extremely high energies, we really dig deep in. Now, really quick for an atom, we have in the center of the atom here, we have protons and neutrons. The protons are displayed in blue, the neutrons in purple, and then on the outside of this arrangement, we have the electrons. Now, the thing to understand about these electrons is they've got a negative charge. And this negative charge drives, basically all of reality as we know of it, but for X-ray fluorescence in particular, it's going to drive how we can see these individual, basically determine what element we have. Now, if you look at the structure, we have two internal electrons in the K shell. We have about 8 in the L shell and 18 in the M shell. This, by the way, continues on as we get bigger and bigger in the atom. The electrons space themselves out in this way because they're trying to maximize their distance from each other, because electrons are extremely negative. So the way I like to introduce this, and this certainly is not representative of UNC, it's purely for comedic purposes, but think of this as your average faculty in a college. And I think of each electron as an individual professor. And let's say they all have very strong egos. And so as a consequence, they try to space each other out in modeling, what type of research they do and all that. What we do with X-ray fluorescence is we send in a $1 billion NSF grant that immediately gets gobbled up by one of the faculty, who then uses it to negotiate a new position over at Yale or someplace fancy, and they're gone. And they happen to be in our inner K orbital. What happens here is we now have a vacancy in the inner K orbital. What are we going to do with that? Like, someone wants to jump in there. So what happens is we destabilize the entire atom, and all the electrons want to jump in, but only one can make it. So with quantum probabilities in place, one electron shifts its position inside this atom, and it is now dropped from a high energy state in the L orbital to a lower energy state in the K. And that extra energy has to go somewhere, and that fluoresces out. This is the same as the photon that comes out with visible fluorescence. Say when a plant is done using the parts of the photon, the blue photon, and it sends out the green. This is the exact same process, except it's happening with the inner electrons, not the outer electrons. So now we have this photon that comes out, and this photon measures the energy distance between the L and the K orbitals. So, and what determines the difference between the L and the K orbitals is how strong the positive charge is inside this atom. That is why X-ray fluorescence measures elements, not isotopes. If I have a couple extra neutrons in here, that isn't going to change anything about the energies in the outer orbitals, because the neutrons have neutral charge. They have no impact on these electrons. But if I change the number of protons, I increase the energy differential between the L and the K electron orbits, and thus the residual energy I get reflects a discrete energy. And this is the basis of X-ray fluorescence as we discuss it. So that is it. Now, some terminology, because as we discussed today in the workshop, we're going to be going over details of this process. So one of the first insider baseball terms you'll want to know is kappa alpha or K alpha. This refers to an L shell electron moving in to replace a K orbital, an electron in the K orbital. So in this case, K is the destination, and alpha, Greek for 1, is how many orbitals removed we are. The number 1 refers to the specifics or the specific structure of the electron that it's shaking out, S, D, subshells, all that jazz. We're not going to get into that, mainly because XRF can't yet fully resolve these individuals. It's possible, and sometimes if you get a strong enough peak in a sample, you will see these differences, but it's actually not that important for the qualitative work that we do. So we're going to keep to the Latin and Greek characters. So that's a kappa alpha. Now, it's most likely that if a K shell electron is being replaced, it's going to come from the L orbital. Again, we're in the realm of quantum physics here, so no one knows for sure where the electron's going to come from. But Vegas odds, it's about a 6 out of 7 chance it's coming from that L orbital. Every once in a blue moon, though, one of the M lines is going to drop to the K orbital, because again, it's just probabilities. In that case, we call it a kappa beta or K beta photon. K indicates the destination orbital, but in this case, it's beta because it's 1, 2 alpha beta orbitals removed from the destination. Now, this is how it works for elements like iron, copper, the kinds of transition metals and alkaline earth metals that we measure all the time. But when we start dealing with rare earths or radioactive elements, we're in a whole different ballpark because we have a lot more orbitals to work with. But the good news is our terminology stays the same. So as long as you understand the basics, you can parse through it. So in the event that an M shell electron drops into the L orbital, we call that an L alpha or L alpha photon or L alpha emission line. Same is true for the N to L. We'd call that an L beta, or even the O to L. We'll call that an L gamma. And this actually continues on and on and on. So this naming structure gets quite complicated. But at heart, the way to remember it is as follows. The first letters, K and L, refer to the destination orbital. The second letter, alpha, beta, gamma, refers to how many orbitals away the original orbital is. Now, I'm mentioning the first letter KL. it is possible to get M-line emissions. In general, in my experience, M-line emissions mean one of two things. The object you're working with is dangerous or you are rich. It's one of those two. It's real. I'm going to give you a quick horror story about an M-line, actually. When I was in Roskilde in Denmark, I was asked to visit a junkyard, which is not usually the place I go. I visited this junkyard, and they had this wall of cars, and there was this forklift that came. Actually, I'm going to stop my share here so we can shift over to camera. So there's this junkyard, and there's a wall of cars, and this forklift comes in and moves all the cars away. And there's like this inner arena. It's like a circular area, and it's got a big lead box about the size of 2 or 3 of the tables I'm at right now. It kind of looked like a place where the Ninja Turtles were going to fight someone. So when we went in, the forklift lifted off the lid of the lead box, and there was just a mass of big black rocks. And I asked, like, what are these rocks? And they're like, we don't know. We had a big steel pipe. The big jaws they have to crunch it basically broke against it, and these black rocks fell out. So we want to figure out what they are. So I measured it with the XRF, and what came back was the M line of uranium. It was pure uranium. So I kind of let back. One of the danger signs with XRF is the detector sometimes measures stuff before the X-rays send out. So if you get a spectrum before you send the X-rays, you're in trouble. In this case, someone had thrown out what appeared to be some kind of nuclear fuel rod. We don't know the full story. We only know that it must have been imported into Denmark because Denmark does not have nuclear facilities in the country. So it was a long, complicated process. They managed to resolve the situation. But in general, M-line means danger or rich because it could be gold, or platinum. So in any case, that's the basics there. Now, what I want to do is take a break here and talk about bananas. Because in intro lectures, we always need an object to sort of wrap around the physical principles to the quantum principles we're going to be working with in the spectrum. So what I have here for our first introductory object analysis is a banana. Now, bananas are supposed to be very healthy for you, specifically because they're supposed to be rich in potassium. Potassium, luckily, is very easily identified using X-ray fluorescence. So what we're going to do is, and I don't know if you can see, there. Yeah, I'm working on it. Here, I can. This is a new experience for all of us here at the University of Northern Colorado. There, is that better? Okay, you can. Great. Now, when I'm measuring the object, just so you know, I won't be able to be this close. But what I'm going to do here is we're going to analyze the banana fruit that is presumably high in potassium. So we're going to put this here. Now, because we're measuring an object that has very low density, right? Most of the atoms in here are going to be carbon or oxygen or hydrogen. What we're going to want to do is use a sample cover cap. That way the X-rays are contained. And unfortunately, you're not going to see my face, but we are going to jump back to the screen, and we're going to see, if I'm lucky enough, if our spectrum is still here. Can you all see the spectrum? Or can you see my grid on my screen? Beautiful. Excellent. So right here, I'm in the Artax software. Just so you know, we're right now broadcasting this Zoom session from the same Wi-Fi network. We're running the tracer. I've never done this before. I really hope this works. What I'm going to do here is I'm going to go to Measurement and Method, and I'm going to choose my light. So in this case, I'm going to do 15 kilo electron volts. I'm just going to go ahead and max current this. And we're only going to do this for 10 seconds, and we're going to do this with no filter. No filter. So, okay. And then, there, that's better. And then I'm going to start the analysis. So good news, it's working. So what you see here is the XRF spectrum for the banana. Now, again, bananas are supposed to be healthy for us because of how rich they are in potassium. And luckily, that is a testable hypothesis. So project, new project, add node, points, and we're going to add this guy and call it banana fruit. All right, so exit, and here we are. So here is our spectrum. Now, every peak you see here is a different element that is present, each color. The only exception is, now real quick, can you guys see my mouse when I move it around? So this peak right here, this really big one near 0, this is one that Brooker adds to its spectrometer that basically spikes it to help calibrate it. You won't see this if you're using an Innovex or a Niton instrument or an Elio. Now, if we come over here, we see all these little peaks down here. If I open up my periodic table, I can click on one of these peaks, and the software is going to give me one of the elements that this could be. In this case, it's aluminum because because we're getting some scatter off the banana. There's not aluminum in the banana, don't worry. There might, however, be a little bit of silicon in the banana because dirt is everywhere. But more importantly, there is phosphorus in the banana. You can see that peak right here. Over here, we have sulfur. And then here, we have 2 big peaks. The first big peak here, when I click on here, I get the following possible elements. Rhodium, which is one of the rarest metals on the planet, ruthenium, which is rare, and technetium, which is not only radioactive, but decays in a state of nature very quickly. You can use it for x-rays in a hospital, but it has to be synthesized. What's going on here? Well, we're not measuring the banana, we're measuring the reflection of the XRF off the banana. In this case, we're measuring the rhodium that we use as our target. See, the thing is, to send any light, you have to have a target inside of a tube. For visible light, when I've got fluorescent light, the target is mercury. You basically put some mercury vapor in the fluorescent tube, electrons smack into the mercury, and then that radiates out and we get visible colored light. Luckily, light bulbs never break, so there's no risk of mercury pollution anywhere. For x-rays, though, we need a very different metal to do this. And there's a number of ones you can use. For example, Niton uses silver. Brooker uses rhodium. There's different philosophies and advantages. Brooker tends to use rhodium because it's so rare that it's obvious to us that it's there. It's also in a nice sweet spot, so that way we know we're measuring something that we want to see. So in this case, we don't have to worry about rhodium, but we're always going to see it. That said, rhodium tells you a lot about your sample. The more rhodium feedback you get, especially the incoherent scatter of rhodium, that tends to tell you have more light elements like carbon and oxygen present in your sample. So this right here is rhodium. Our next peak here, it's a little guy, that's argon. Argon is a noble gas. What in the world is that doing here? Argon is present because it's less than 1% of the air that we breathe. It's about 0.98% of Earth's atmosphere. So we're measuring the argon molecules in the air between the detector and the banana. You're always going to see argon. Sometimes argon can tell you about the porosity of the object you're analyzing if you've got a lot of empty air pockets near the surface of the object. But normally it's not too helpful. But it can be used as an indicator for if you're close enough to the object. And then our next big peak here, this is a nice classic K alpha, K beta pair. That's our potassium in the banana. So yes, it is true. There is potassium in bananas. Happy to report. This is our K alpha. This is our K beta. This is the L to K transition. That is the M to K transition. So that is our banana. But here's the thing. So my wife works in Kibale National Preserve in Uganda, and she works with chimpanzees. It's kind of funny at our house when there's gossip. I'll kind of walk in and people will be talking about this or that chimpanzee, kind of like it's a social network thing. So we've got a lot of favorite chimpanzees in the house, and one, Takugama, who is just the worst chimpanzee on the planet. This chimpanzee throws logs at males when they visit the preserve because it sees even human males as competitions. It's hyper aggressive. Anyway, well, you'll hear more about that if you attend my wife's class, if you're a UNC student attending this. But in any case, when you watch chimpanzees in the wild eat fruit, they don't peel fruit and eat just the insides. They also eat the outsides. And that got me wondering about the nature of the nutrition of this guy. So right now I'm taking the banana off. I'm going to stop share. We're going to go back to the camera. So right now I've removed the banana fruit, and now we're going to switch with the banana peel. And we're going to see if that tells us anything that's similar or different. All right. and we're going to come back to sharing. Just as an aside, I can't believe this is working so far. Maybe I spoke too soon. All right, here we're back. So now we're back over here, and in red, we have our banana fruit. I'm going to start measuring, and this next spectrum will be colored green, and this is going to represent the banana peel. So 1, 2, 3. And we're still connected. That's good news. All right, so you can already kind of see what our takeaway here is going to be, can't you? So here in red, our banana fruit, we can see that the peak of the potassium is about equal with the rhodium from our tube. There's a lot more potassium in this peel. In fact, almost twice as much. Now, real quick, what I want to focus on here is what in the world are we measuring? We're measuring the photons that come back from the atom. So if let's share over to the presentation once more, wherever that went. Here it is. All right, so if we go back to our presentation, let's revisit what's happening when we hit start. First thing is we're sending in a photon. This is what the XRF is doing. This, for example, is going to be our potassium atom. We're exciting that atom or that electron, and that electron is out of potassium. And then an L orbital electron destabilizes, drops in, and then the energy of the difference between those two orbitals is released. Here's the important point. One photon is evidence for one atom. Makes sense, right? One photon comes from each atom. So when we go back to our spectrum, here, there we are. So when we see our spectrum here, we're seeing the total sum of atoms of potassium detected. So the way to interpret this qualitatively, by the way, this gets a lot more complicated when we get into the depth of statistics, but to keep it very superficial at this point, we're measuring more atoms of potassium in the peel. So in this case, the peel is actually much more nutritious than the fruit. We don't eat the peel because it's bitter, because again, it's nutritious, and we tend to interpret nutritious stuff as kind of bitter, and so we eat the nice sugary insides instead. So if you really want potassium for your bananas, you know what to do. But that's not all. Do you notice here in green, there's another peak showing up? It's just a little to the right. That is calcium. So we know that the banana peel is rich in calcium too. So in any case, if you want potassium from your bananas, you need to eat the whole banana is really the takeaway here, just like a good chimpanzee. But the good news is there's other foods that we eat that are different. And so that's going to bring us to our next step. We're going to take the peel off. We're going to stop sharing, and we're going to return to video. Now, what I'm going to do real quick is I'm going to set up our object here. Add spectra, remove object, and this is banana peel. Our next object is going to highlight a difference. So spectrum, close spectrum. There we go. So our next object is going to change things a little bit because we're going to measure a little bit of coffee. Now, coffee is one of the most favorite drinks in all the world. It originates from Ethiopia about 1,000 years ago. The legend has it an Ethiopian herder noticed his goats were getting a little uncontrollable and excited when they were by a coffee tree. And he discovered the wonderful properties of coffee, which then just took the world by storm from then on out. What I'm going to analyze here are dry grounds of coffee. And I'm just going to add a pinch here because I want a control sample for interpreting our banana. So we're going to go back to sharing the screen. So share screen. Back to our spectrum. And I'm going to measure the coffee the same way. Once again, we're going to put the protective sample cover on because safety first. And I'm going to hit start. And we're going to measure the atoms of potassium in coffee as a control for the banana. And coffee is going to be in blue. All right. So, as you can see here, coffee has what would you guys say that is? Like 4 times, 5 times as much potassium as the banana peel. Potassium coffee is absolutely loaded with potassium. So if you drink a big cup of coffee in the morning, you're probably getting much more potassium than you are from the banana. To boot, the potassium in coffee is already digested for you. It's dissolved into liquid, right? So it is immediately absorbed by your body. And my pet theory is, and again, this is way outside my expertise, but my pet theory is that when we talk about coffee, people talk about caffeine and how they need it, but potassium's a neurotransmitter. And you're just loading yourself up with like this, positively charged alkaline, that's absolutely incorrect. I'm speaking too fast. You're charging yourself up with a neurotransmitter in addition to the caffeine. So I often like to imagine that that's actually one of the things you get a buzz. I discovered this because in Europe, you often have a cup of coffee after dinner. And so I'd have a cup of decaf coffee because I didn't want to, stay awake all night. But I stayed awake at night all night anyway because I was getting buzzed from all the potassium, not the caffeine. So in any case, if you have coffee, this is what's happening. By the way, if you ever want to teach X-ray fluorescence for your class, the next step, which we can't do here because we're outside and we're still in the virus apocalypse, but you want to percolate the coffee and then measure the grounds. What you will find is there'll be much less potassium in the grounds than there is in the wet grounds and the dry grounds because it all dissolved into liquid. So that is the basics of it. Now, that kind of takes us on a tour. The key thing to remember about this, in addition to drink lots of coffee, is what the primary effect you're seeing when you measure with X-ray fluorescence is the excitation of atoms. So in this case, the physical manifestation of the atoms in the potassium peak. Now, by the way, there are other things that come along. I'm actually going to add some potassium back to this. And what we're going to do very quickly is we're going to tour the different ways we can measure with the XRF, because it isn't just, right now we're very focused on the light elements, but that isn't the only thing. So I'm going to add my spectrum here, and I'm going to kick out the ones I already have. We're going to call this coffee grounds. Yes. Can you unmute? Yeah. Yeah, just a sec. We've got a question coming up. And if you're having any problems, I can try.
Okay, yes. So the question is, how do you decide the settings for each assay?
Actually, who's that from?
That is from Anonymous.
Anonymous. Great question, Anonymous. So how do we choose the settings? Well, so the answer depends on what your question is. I'm going to switch this over to camera real quick. So we're going to stop share. And I'm going to reorient this towards me. So to answer your question, Anonymous, the answer is it depends on your question. In fact, that's generally my answer to every possible choice you have. What are you trying to learn? Now, for me, generally speaking, and everything I discuss now, we're going to immediately roll over and test with our coffee grounds. The first question is, what are you looking for? If you don't have an answer to that question, if you're just using this to explore what's in an object, which, by the way, isn't just an acceptable technique, but is my favorite technique, you want to do what's called lab rat mode, which is all the possible energies without any exclusions. That's going to be 40 or 50 kilo electron volts, and a lot of that depends on the regulations of the country you're in, or whatever relevant legal body is present, as well as But that's basically, the more energy you send in, the more elements that you can see, and you're going to want to use no filter. So we're not going to filter the beam at all, and that's what we call lab rat mode. And I typically only do this for about 10 seconds because you're going to have a lot of feedback from whatever you're analyzing. This technique is great because you can see a little bit of everything. It's bad because you're also going to be maximally exposed to backscatter. So you're going to have the worst detection limits for everything, but you're also going to have the most flexibility. You can think of this as a general mode. So let's jump back over to our XRF. And what we're going to do here, I'm going to clear the screen. I'm going to bring up our coffee grounds. So our coffee grounds, I measured 15 keV because I knew I was interested in light elements. So I'm going to go to measurement and method. And now we're going to change our energy to 40 keV. We're just going to be a little bit on the safe side. I don't want to do 100. Let's do 50. Let's do 30. Now the current real quick. Voltage determines the range of elements that I see. Current is basically how much light do I send in. If I send in a lot of light, I have a better chance of seeing elements more quickly. If I send in too much light, I can blind the detector and I can cause some problems with the actual spectrum. So it's a little bit of a balancing act. My general rule is high current for low density and low current for high density. So you want to be inverse of the density. So if I'm exploring, let's say, coffee grounds, most of this is carbon and oxygen, I really want to make sure I'm doing low energy. If I'm analyzing the ground I'm on right now, I would actually be doing the same thing. I'd be doing high energy. Because, does anyone know when you're walking outside on the ground what the number one element underneath your feet is? By both volume and weight? Oxygen. Silicon dioxide, right? So there's 2 atoms of silicon, 2 atoms of oxygen for every silicon. So basically in our everyday life, we're walking on clouds of oxygen. They're bound by various metals. So that would be low case. Now let's say I'm measuring King Tut's dagger from space, his meteoric space sword. If that's the case, I'm analyzing a metal, and the metal is going to give me a lot of feedback from the XRF. That's when I'm going to want to have a much lower current. So for lab rat mode, you want to kind of adjust your current to what you're dealing with here. I'm going to go with 30 because it's a nice middle ground, but I could go higher if I wanted to. But the key thing here is no filter. So I'm going to hit OK, and I'm going to start. Now in red is our 15 keV spectrum, and in green is our 40 keV spectrum. And what you'll notice immediately is we've got a lot more photons out here by 20 keV. You'll also, do you notice that the potassium peak for the exact same coffee grounds is half as high as it was before? When I reduced my energy to 15 keV, I'm focusing on potassium. So the exact same object gives me a higher signal because I'm not wasting all my X-ray photons on different parts of the spectrum. But if I'm doing lab rat mode, I can see more peaks out here where my other spectrum trailed off. So in this case, I see these 3 over here. These I like to think of as the 3 amigos in the XRF spectrum. I'm going to start in the middle. We're going to open up our XRF periodic table, and in the middle, I have rhodium, K alpha. This is the K alpha peak of the rhodium in my X-ray tube. This is always going to be at 20.2 kiloelectron volts, or keV. Always, always, always. It will never change. If your XRF sees it at a different energy, send it to the XRF doctor because something's wrong. So you'll always see that peak there. And you're always going to see it because rhodium is physically in this instrument. If you're working with a niton gold plus instrument, you will see it at silver instead. So it'll be a little to the right, around 21. But in general, whatever your tube is, you're going to see that. Do you see the big peak to the left of rhodium here? That is also a reflection of our rhodium. But here, rhodium, let's think about what happened here. There's no rhodium in the coffee grounds. So my rhodium from the X-ray tube went in, it bounced off of carbon or oxygen, and it came back to the detector with the exact same energy as it left with. So it sees it as a rhodium photon. That's what we call elastic scattering. That's Rayleigh scattering. Do you remember when we were looking at the visible light spectrum and we were talking about why the sky is blue? That was also elastic scattering. The blue light from the sun enters our atmosphere and bounces around elastically, so then we see the blue. This is like the sky. This is like the equivalent of the sky in the XRF spectrum. It's the thing you always know is going to be the same. To the left is our Compton peak. That is the inelastic rhodium scatter. These are all the rhodium photons that bounced around in the coffee and the oxygen, and they lost energy when they returned to the detector. And they form kind of this Gaussian normal distribution. That's one of the ways you can tell it's different. It's a much wider peak. It's about 2 or 3 times the width as the elastic peak, because this isn't a peak in the same way. It's a Bell distribution of all the photons that lost energy. To the right is the similar phenomenon, but in this case, those photon-electron interactions gained energy, and so it's a higher energy Compton. The higher energy Compton, by the way, always has to be lower than the low energy Compton because we can't gain energy in this process. It's against the law, specifically the law of conservation of energy. So in this case, we are the low energy Compton peak is always the highest energy. By the way, if you were ever building a quantitative calibration with XRF, some people like to use the Compton peak to do their normalization to. This is a bad idea because Compton is very responsive to light elements that are present in the sample. The more carbon and oxygen, the more your Compton goes up. So if you're calibrating to rocks that happen to have carbonates, you're just going to have some trouble. The really good thing to normalize to is the Rayleigh peak, the Rhodium, the elastic scatter. It's a little more neutral to the effects of density, and so your calibrations will be less influenced by surprise unknowns. But in any case, those are those three peaks. But if you look, there's this peak over here. That right there is rubidium, RB. What in the world is rubidium doing in your coffee? That's a weird metal, right? But it can be explained. If you look, the element right of can you guys see the periodic table and the letters on it? Great. We've got a couple people here watching, about 20 feet away. Right above rubidium is potassium. Here's the thing. Rubidium, like potassium, has one valence electron in its outer orbital, which makes it very reactive. Also, it's got a similar ionic radius to potassium. So the coffee plant, when it was absorbing all the potassium from the soil, by the way, coffee plants grow really well on volcanic soils, like in Ethiopia in the Great Rift Valley, or Kona, Hawaii, which is a volcanic island. That's because basalt has lots more potassium than the granitic rocks that make up most continental shelves. So that's one of the reasons why you see all that. You see that's why coffee, because really coffee is just, it needs potassium like nothing else. So in any case, with the potassium, some of the rubidium came on as a straggler. So rubidium in this case is a hitchhiker element. The plant process, the coffee plant knows it wants potassium, but all it can do with evolution is grab elements with this charge and this ionic radius. And rubidium fits that bill too. So we have a little bit of rubidium. But if you look here, the rubidium peak is really small. And below it is all this backscatter. This is the stuff that causes problems in XRF analysis, right? Because this is all the photon-electron interactions that don't have an easy explanation that are going on in the background because of our choices in geometry to make this instrument handheld. So we have to find a way to eliminate that background. So to do that, we need to use what we call a filter. So I'm going to add spectrum. We're going to remove that object, and we're going to call this Coffee Grounds Lab Rat. Great. So now we've got that peak right there. So what I'm going to do here is I'm going to close all these spectrum, and I'm going to bring back our 40 keV spectrum. And there's our rubidium right there. By the way, we've also, that's nickel from our X-ray tube right there. Let's finish our tour here. That right there is nickel from an X-ray tube. What in the world is nickel doing in here? Well, that's the casing that's around the XRF tube. So we're going to see some of that. And then over here, we have iron. And then over here, we have manganese. These two guys we didn't see earlier because our 15 keV light spectrum just wasn't high enough energy to get those guys very excited. But now with 40 keV, we're doing a much better job exciting them. If we dig real deep, we'll see that they were there, but they weren't as easy to see. So there we have manganese, iron, nickel, and rubidium as our elements of interest. Let's add rubidium here too. What I'm going to do now is I'm going to go to measurement, method, and we're going to use a filter. Now what this is going to do is the tracer is going to spin a little wheel, and it's going to insert a filter that is made of 25 microns titanium and 300 microns aluminum. The reason we do this is the titanium is going to attenuate the XRF beam and block a certain range of energies from going in. The problem with using titanium is I'm going to add a titanium peak to my spectrum, which no one wants. So I use the aluminum behind the titanium to scrub it, and that way I erase the signature of my filter. So I'm going to click OK. So now everything's the same energy, same current. All we've done is we've added some metal between the XRF beam and the coffee. So let's start. So what you'll notice here immediately You see this giant nickel peak that was here? It's almost completely gone now. The filter has blocked the nickel from the XRF tube from getting in. So now we don't have the instrument interference. That's another one of the problems with using the lab rat mode, is when we do a lab rat mode, we see all the atoms around us, including the atoms that make up the instrument itself. We can't avoid that. If we could make an antimatter XRF, we'd go for it. But unfortunately, we can't. We have to compromise. And so there have to be some metals present in the instrument. We get around that by using filters to really minimize that impact. So that's good. And we can now see the iron and the manganese that is present in very small quantities. If you look here, you can see that our rubidium peak is much better. Try to face camera. All right, gotcha. So I'm showing the screen, right? Okay, good. Yeah, good. All right, thank you. Yeah, so in any case, what we can see here with the rubidium is the rubidium peak is now a little more visible. Let's really zoom in on this part. So here it's a really noisy view of the spectrum, but what I'm going to do is I'm going to spectrum normalize here. So in green with our filter, you can see that our rubidium peak is now twice as high as our background. So we've doubled our noise. We've basically cut in half our signal to noise ratio. Or we've doubled our signal to noise ratio. So that's good news. So the filter helped us see that rubidium, and when it came down to iron and manganese, it knocked it out of the park, right? Our baseline is 0. And if we look, what our filter basically did is it's like Cookie Monster taking a bite out of the cookie, right? Like we just took a bite out of all that excess radiation that was causing us all those problems. So now we have a nice clear baseline at the bottom for which to compare all of these data to. So the problem is for iron and manganese, we've met our goal. We've done a great job. For rubidium, we still have a lot of background noise. You can see that over here. So we actually want to up our filter game a little bit. So what I'm going to do here is let's first add our spectrum, add spectrum, remove that guy. We're going to call this coffee grounds TI filter. So let's close our spectrum. And now our titanium filter measurement is going to graduate to red. I'm going to go to measurement, method, and we're going to switch over to 75 microns of copper. So now what copper is going to do here is what titanium did. Copper is going to take another bite of the spectrum. Then the problem we have is we've got copper in the spectrum. So we then use a layer of titanium, which we know can take out the copper, but then our problem is all that titanium is now in the spectrum. So then we use the aluminum to take out the titanium, and we're home free, and we've got a clean shot. So, by the way, this is the way Brooker does it. Other companies use different filters. So one thing you'll want to be cognizant of is knowing what the filter composition is, so that way you know whether to identify what is being added to the spectrum if they don't do the stacking technique. That said, if you have an equipment that doesn't tell you the filter, because unfortunately a lot of companies treat this as very proprietary information, what you can do instead is you can measure a water bottle filled with water, or a 10-carat diamond, which is made of pure carbon. The reason you do this is the spectrum there isn't going to add anything. There's no metals, there's nothing in there. And so whatever you see is going to be your instrument contaminants. So if you need to figure out what's in the filter of an XRF instrument that you're using, the water bottle / 10-carat diamond test can help you identify what is there. All right, for now we're going to add our copper filter in. I'm going to click OK, and we're going to start our assay. So in red is the titanium filter, and in green is the copper filter. What you'll notice right away is our spectrum signal is getting a lot weaker. Because we're adding a lot more metal in the way, we're really starting to obscure the spectrum. This is where a high current really helps us. So I'm going to go measurement, method, and we're going to up our current to 50. And I'm going to take the exact same measurement with the heavier duty filter. And what you'll see here in pink is that we have the exact same filtration, but now the signal we're getting for each second is much stronger. So as you add filters, you want to start to reduce, you want to increase your current. So we're going to get rid of that bad current spectrum, or both of them. Let's add spectra here. remove that object, clear these guys, and then coffee ground CU filter. All right, so now I'm going to add the titanium filter in red and the copper filter in green. What you see here is if I'm looking for rubidium, we've got a really clear peak here now. Our signal to noise ratio is fantastic. So right here, I can see rubidium. In fact, that's not the only thing I can see. If I click right here, I can now see a little bit of strontium, SR. Strontium is to calcium what rubidium was to potassium. It comes along for the ride. So now we see these elements much more clearly. So Anonymous, I hope this answers your question for why we want to use filters. With this filter, I now have a really good signal for rubidium and strontium. The problem is my signal for manganese and iron, it's a lot weaker, isn't it? I don't see them nearly as well. So when I've gained in rubidium, I've lost in manganese and iron. So to come right back around, this is why the selection of your filter, your energy, your current really depends on the question you're trying to ask. If you want to show your students whether or not potassium is in the food they eat, you want to do the 15 keV measurement because that really amplifies your light elements. And you want to use no filter because you're dealing with all light elements. The second you use a filter, you lose all of them. If you want to look at transition metals like manganese and iron and copper and nickel, a lot of the really common ones, you want to use that titanium filter because it really balances the trade-offs. And if you want to look at heavy elements like rubidium or strontium, stuff that's a lot more rare, that's present in only a few parts per million, then you want to use a copper filter, whether it's 75 microns copper or 100 microns copper. That just determines sort of how much of a bite you take out of that spectrum. Now, physically, what's going on here? Well, it comes back to plants. So let's stop the share here, and let's restart back over to our presentation. Now, earlier, at the very start of this lecture, we talked about color fluorescence. When we're talking about color fluorescence, we were specifically talking about why the sky was blue, all that Rayleigh scattering, and why plants were green, because they take in that blue light and they fluoresce the green. The thing here is we have to send in more energy than we get out, right? I need to send in enough light to activate the chlorophyll, so I send in the blue, but then I get back the green, which is the color of the plant. You need more energy to excite. Well, in our filters, we're doing just that. So let's exit, or let's stop share, exit out of here, and let's restart our share over at the spectrum. So when I look at the spectrum, the red spectrum, which uses the weaker filter, you can see that the 0 point for the filter is about here at about 7.6 keV. That's when we hit 0 XRF signal. So here, the filter has blocked all of those X-rays from getting through. But what is exciting iron and manganese are all the photons to the right in this big red bubble over here. All that scatter, those photons ping the iron and manganese atoms and make their signal high, even though there's no activity right in the energy vicinity they're in. Because remember, high energy excites lower energy. For rubidium, all I did is I moved all that scattering to the right. And now I've got my background measurement there. So your key zone of interest, the area where you're going to be optimized to see elements with the lowest possible, with the highest possible sensitivity, is going to be right before the wave. I like to think of it as like a surfer, right? If you're surfing on the California coast and you want to ride a wave, you don't want to be on top of the wave. You don't want to be behind the wave. You want to be right in front of the wave so all that energy propels you. It's the same with the elements in an XRF spectrum. You want your elements of interest, like rubidium and strontium, to be right in front of the wave of all the scatter, because all that scatter is going to increase your ability to see them, but then your filter is going to minimize the background underneath them. So that way you get the perfect balance of energy moving in the right direction to see it. So that's really how you identify it. So if you're dealing with a targeted study, so for example, a good colleague of mine he was going to join us today, but he just found out they're expecting a child, so they're very excited and focused on that right now. I think they found that out about an hour ago. But he's working on a project where they're going to source coffee beans from an archaeological site. It's in San Francisco. They found some coffee beans, and they want to identify if the coffee beans are coming from Hawaii, from Ethiopia, and all that. But to do that, we've got to identify the elements we're interested in. And in that case, it's going to be rubidium and strontium for the reasons you just saw. So in that case, we always use the really aggressive filter because we know what our question is before we start the analysis. We're looking for these elements in particular. If you don't know, go back to lab rat mode, 40 keV, no filter. You've got a wide open spectrum to see everything. So that gives you that ability to see everything. And if you're looking for light elements like phosphorus and sulfur, then you're going to want to use no filter, but you don't want to send in all that extra energy because that's just dead weight in your spectrum. You want to compress it to 15 keV, or even I've had some success with even 9 or 10 keV. It depends on the other elements that are in the spectrum that can consume that signal. So in general, the three modes are for transition metals and heavy elements, use a filter, 40 keV or 50. If you don't know what you're looking for, lab rat mode with no filter, but still 40 keV. And if you're looking for light elements like phosphorus, sulfur, potassium, no filter, anywhere from 10 to 15 keV. And that's basically it. With those three modes, you can probably do 95% of your XRF work. We can get into really exciting hypothetical filters, like filters that can let us see cadmium and arsenic to just 1 ppm. But I think for our purposes, this level does pretty well. But if you have a much more specialized study that you want to question, feel free to email me at b.lee.drake@gmail.com, and I can help you walk through the specifics of that as you work on that. So I hope that answers your question, Anonymous. That's what guides our choice of features. Now, just to give you a heads up, when we move over to analyzing museum artifacts, what we're going to want to do is we're going to want to use general mode to start with because we don't know what we're going to see, right? It could be arsenic, it could be lead, there might be chlorine, right? That's one of the challenges. If you have a salt wash, if I use a filter that's optimized to see just arsenic in a museum collection, I'm going to rub out all my chlorine, and then I'm not going to have my alternate hypothesis to confirm. So, and by the way, if there's arsenic in a museum object or mercury, there's going to be no ambiguity in the spectrum. It's going to be like a massive spike. So, so we're going to be using general for most of today. But generally, you start with general. As your questions mature, then your analysis can winnow down. So I hope that answers your question, Anonymous. Andy, do we have any other questions?
Question again about your website that is in there?
Yeah, www.xrf.guru, G-U-R-U. It's not named after me. I named it after Bruce Kaiser, who invented the first handheld XRF systems. Nope, .guru. b.lee.drake@gmail.com. Yeah. Actually, while you find the question, one quick funny note about my email. We published an article in PLOS One a couple years back that we were really excited about, and we had to issue a correction to the article because the editor put my email as b.lee.drake@gmail.edu, which is not possible. So anyway, always check your email address when you're publishing papers.
I don't know. Gmail EDU might be coming towards us soon.
Yeah,
like we're all
I know, right?
We're all on
man, another year of this.
Zoom, is it going to be Zoom.edu? Anyway, the question says here, you said earlier that normalizing to the Compton peak was not a good idea,
yes,
as it is dependent on the density of the sample material.
Yes.
I was under the impression that normalizing the Compton lower energy peak was done purposely to account for the density of the object and quantification of the composition. Can you elaborate?
That's what they think they're doing. That's not what they're actually doing. Compton's too much of a moving target. So, other XRF specialists might disagree with me. But I say this having built probably hundreds, possibly even a little over 1,000 calibrations. Everything normalized to the danger here isn't accuracy, right? I might get a very good R-squared or high-performing calibration if I use Compton. The problem is generalizability. How do I handle unknown examples when I'm out in the field analyzing? That's really where I run into difficulties. And Compton is just much more sensitive to those changes than Rayleigh is. So I can't go into a lot of detail about this because I've got a lot of NDAs with mining companies. But in general, when you're dealing with when so let me give you a hypothetical here. Let's say you're an academic, you have a budget for 100 ICP-MS standards that are hyper-tailored for exactly the matrix you're looking at. Maybe it's a specific rock type, maybe it's lead-glazed ceramics, but either way, you are 100% confident that all you need to do is measure this one exact matrix type. Then a Compton normalization can work pretty well, because the Compton's going to reflect those changes that'll get passed on to your element identifications. But let's say I'm making a rock calibration that might get some limestone, that might get some mudstone, that might get some granite, that might get some basalt. In that case, the focus needs to not be accuracy in the calibration standards, but in generalizability to other rock types. And in that case, Compton becomes a major hurdle for me because I've added all this extra variation in normalization to my calibration. So in that case, Rayleigh makes a lot more sense because it just means you're staying away from that. In fact, I oftentimes will do a little bit wider of a window for the Rayleigh just to make sure the counts are high in that range. But that's the reason for why I make my comments about Compton. And I'm not saying don't use Compton. There are cases where it can be useful, but I would not make it my default, if that makes any sense. Because in general, the path I always see people take with this equipment is they have an idea, they make a calibration, but then the scope of their project expands once they're gathering data, and now they want to measure a little bit of this, a little bit of that. And once you start doing that, your calibrations really start to suffer when we normalize to those things. So I hope that answers your question. Who's the question by again? Anonymous. You're very chatty today, Anonymous. But in any case, that's my rationale for avoiding caution on Compton. All right. Any other questions we have, Andy? All right.
Yes, we can take some open questions at this moment if anybody has any about the presentation or your specific, situation. Could take a few of those.
Yep, that works. We're going to stay online with the chat. I think we're going to start getting set up now for analyzing some museum objects. Is that all right, Andy?
Sounds good. Yeah, it might take us a while to get started, but anyone that wants to tune in later will be live streaming our testing. We won't be doing tons of instruction, but we can try to take some questions, and you'll see what we find. Yep.
So we're going to start that at 12:30 our time, so in about 45 minutes, right? So in about 40, we're going to take a 45-minute break. We're going to leave the Zoom session open. I'm just going to turn off my camera. We'll have the chat box open. I'll be checking that periodically. And then when we come back, we're going to have a whole bunch of objects. The Zoom session is going to get complicated because we're going to have someone manipulating the camera. We're going to be switching back to the computer. So it's going to be all kinds of fun. But we'll stay available for questions as we set up. And if you don't have any questions, hang tight for about 45 minutes and we'll be back with you.
Okay, we do have one question just came in. Before I address that, I just want to thank everyone. I know some people won't be able to come back, so let me just going to try to pull my screen up.
And we will be recording this, right? So we will be recording this, so it'll be available later as well.
Can you shut off your screen share for the moment?
Yeah.
Just a moment. I'm going to pop in with my video. Thank you. Hi, everybody. I just want to thank you so much for attending today. I really appreciate your participation in this event. As I say, we will be live streaming some testing for several hours that may or may not be compelling TV. I personally always get excited, no matter what it is, just to see, what's in it. Sometimes nothing remarkable, sometimes arsenic and lead, and sometimes some interesting thing. And we're very fortunate to have Lee here. As you've seen from his presentation, this is a remarkable tool that many of us are familiar with, but we can always be more familiar. And the more you understand the science of what that machine is doing, the more capable you will be at collecting and interpreting your data. So personally, in my own work, I always recommend whenever you're doing some kind of testing like this, you really want to consult with someone who knows their stuff. Otherwise, you could make some really naive interpretive mistakes. And that comes out at the conference when you say what you found and someone in the back goes, that's actually what's in your test tube or something like that. And you realize, oops, you made a rookie mistake. And that's okay. But the more you can consult and watch these kinds of webinars, I think you can be more confident in your own testing or the reports presented to you by others, right? A lot of times we're commissioning something and we want to know how to interpret it. So thank you so much for participating. We will be, as I said, taking questions during some of the live stream later. If you have any other questions come up, you could email Lee or me. You should have gotten an email from me or Dr. Hamilton with a link to this conference. So again, thank you. I'm going to pop out with this question here. Okay, so when will the recording be available? And question says, I haven't done physics since high school, so thanks for the explanation. Very accessible. Yes, I'm not sure exactly when, probably within a few days to a week. I will get it together and I will see where we can host it, and I'll send an email link to all participants with that video. And then I will read this question, and then I'll pop out of the way. Question from Ray Sumner at the CSU. Are there any filters you would recommend for analyzing historic lead bullets?
So let's unmute historic lead bullets. I worked on a project similar to this with some folks at Grand Junction. I should probably put you guys in touch, actually. You guys have similar interests. For lead bullets, your big challenge is going to be lead. That's actually going to be a massive challenge because lead is one of the most dense metals available for XRF. And one of the problems we run into with lead is it's so dense that when we build calibrations with it, our calibration curves are parabolic. Because as your lead increases, your lead peak goes up, but then your lead gets so dense it starts reabsorbing the X-rays when they're emitted, and so the higher concentration starts to bend back down in a really frustrating way. So I think it really comes down to the questions when you're looking for lead bullets. I'm guessing it's going to be the trace metals in the lead that are going to be most informative. Things like copper, tin, along those lines. I would say the first thing is, my comments about lab rat mode. I would stay away from lab rat mode for all that I could, because the density of that is going to give such an intense feedback to the XRF that you're really going to have issues with spectrum quality. That said, use the most aggressive filter you have. That's generally 100 micrometers in Brooker instruments. I don't know what that would be with nighttime, but you'd want to use whatever is tailored towards the sort of the most heavy-duty instruments. So yeah, use the heaviest possible filter you can. Drop your current to as low as you can. And this sounds counterintuitive because it means your count rate is going to be very low, and just measure for about 4 to 5 times longer than you would normally. So if you normally measure for a minute, maybe do 5 minutes at a low current with an extremely high filter. And that's going to give you the best accuracy for these trace metals that are present there. Now, with lead bullets, there's a trick you can kind of do to get around some of it. The L-alpha line of lead fluoresces at about 10.5 keV. So if we send in, let's say you're interested in light elements that are on the surface of this lead bullet, if you send in 10 keV, you're actually going to starve the lead L-alpha lines of any energy to fluoresce. So then you can drop back down to measuring the light elements like phosphorus and sulfur. Well, not sulfur for reasons we'll get into in just a second. But then you'll be able to measure the light elements without interference from the lead L-alpha line. The problem is you're going to have the lead M line at about 2.4 kilo electron volts of energy. So when that happens, what you're going to want to do is you're going to want one spectrum of a pure lead object, which is actually very cheap to acquire. Lead is not an expensive metal. Am I not recording? I think we're good. I'm still live over here.
Okay, good.
So I'm going to keep talking. I can always repeat if we've lost folks. So in any case, so with lead, the problem you're going to run into is the lead M line is going to almost perfectly overlap with the sulfur K line. This is one of the big challenges actually in measuring historical pigments, because if I've got a painting, let's say I'm looking at the Mona Lisa, they use lead-based pigments, but sulfur is very important for a conservative to know about because it's so reactive. So what you do is you get a pure lead object, so just pure lead. You measure that with the exact same parameters for lead elements, and then what's going to happen is your lead M line is going to be in the same place, but if you have sulfur, your peak's going to be wider because it's still there. It's just part of what's measured there. So in that case, it's the width of the peak, not the height of the peak, that's important. This is a qualitative application. It requires detailed spectrometry work, but it can be done. But that'll be the challenge. So to recap, transition metals in a lead object, and by the way, everything I'm discussing here would also include lead glazes for ceramics because it's still lead. So 50 keV, low current, and heavy filter, and lots of time for analysis. That's going to cover your transition metals and anything else you're looking for. And then for light elements, 10 keV. I might even bump that down to 9, even though you might make iron suffer a bit in that case. But bring it down to 10 or 9 keV. And then for sulfur in particular, you're going to have to look at the width of the line, not the height of the line, because of its overlap with the lead M line. Hope that answers your question, but it is doable. It is doable.
I'll pull that over so you can see if any more questions come.
Okay, perfect. I'm going to hang here with y'all, so I'll be here available for other questions. They're going to start getting set up for the main portion of today, which is where we're going to be analyzing objects. So, yeah, we're gonna hang tight and get set up. Feel free to ask questions. I'll be checking in periodically, or all the time if there's lots of questions, and we'll go from there. So, for those of you who want to take a break, take 30. We'll be back at 12:30 Mountain Time, 12:30 Mountain Time, 2:30 Eastern Time. I'm so bad at this. 11:30 Pacific Time. And if you're in Europe and you're staying up really late, we will be recording this if you want to watch that later too. So thanks. I'm going to hop off real quick to save the recording, and then I'll be back. All right. Excellent. I think we've got that. Are there any more questions? Great. Yeah, I just turned it off so I can save that. Yeah, I can restart it on mine. I just want to make sure it's saved.
So is this the stuff that's coming over here?
Huh?
This is different, like granular.
That's the coffee.
Oh, okay. It's like roof material or something.
Yeah. No, that's the coffee. That's the coffee. I blew it. Just because it's easier than touching the XRF.
Okay.
So, funny story, by the way. Once I had to measure a rare earth powder. It was like a neodymium powder. I put it on the XRF, but there was a tear in the window. So all this rare earth powder dumped on the $9,000 detector, and there was always rare earths in every spectrum. It was contaminated. So I was in trouble for that one.
I think you might still be broadcasting.
I am.
Okay. So
Yeah.
Just so you know.
Yep. Nope. I was going to leave this on while we get set up. So if anyone wants to jump in with a question, I don't have to restart the broadcast. All right. Yep. Nope. I am not sharing anything. I probably shouldn't have talked about all the uranium in Denmark, but that's okay. All right.
Okay. So we need to bring up stuff.
Yep. And I'll hang here. Where's your computer's right there, so I can check that. Yeah. No, definitely.
I got a couple of thank yous. I lost some rhythm, so you shut down on me.
No worries. Oh, I see. I think. Oh, okay, good. So my chat thing is current. Yeah, I can see it. Yep. Q&A. I just have the. I just have a chat window with all panelists. Okay.
So, yeah, you want to check this too?
Yep, I'll do that.
Probably if we can get a break right now.
Yeah, no, that's great. I'm going to